In the latest federal operating update, the Bureau of Reclamation confirmed that additional water is moving from Flaming Gorge toward Lake Powell, with as much as 1 million acre-feet scheduled to travel south by April of next year. One signal would be unusual. Several signals together are harder to dismiss. The probable minimum forecast placed Powell inflow near 31% of average. Federal operators reduced the water scheduled to leave Glen Canyon Dam. Flaming Gorge began releasing part of its own stored reserve, and every adjustment is aimed at protecting a critical elevation at Powell, 3,490 feet above sea level. But that is not the most dangerous part. The headline is the water entering Lake Powell. The hidden number is the operating margin that remains above the machinery inside Glen Canyon Dam. A reservoir can still hold billions of gallons and lose part of its ability to move that water downstream. This is not just a reservoir release. This is a system buying time with water it cannot replace. Powell may rise while the Colorado River basin becomes no wetter. So the question is no longer simply whether Flaming Gorge can help Lake Powell. The question is, what happens when one reservoir must spend part of its own protection to preserve hydropower, downstream releases, and critical infrastructure at another? Like, subscribe, and comment where you are watching from. Because this water is not only moving through a river, it is moving through the shrinking safety margin of an entire region. At the beginning of this operation, the first warning did not arrive as a siren. It appeared as a change in the way federal water managers were moving water through a network of dams, reservoirs, rivers, turbines, and forecasts. On April 23rd, the Bureau of Reclamation began drought response releases from Flaming Gorge Reservoir, sending additional water into the Green River on a journey of roughly 455 river miles toward Lake Powell. The decision came with an extraordinary operating range. Under the federal plan, Flaming Gorge could provide approximately 660,000 to 1 million acre-feet of additional water by April of next year. That is the first light on the control board. But it is not the only one. Months earlier, on December 1st, federal operators had already begun changing monthly releases from Glen Canyon Dam so that more water would remain inside Lake Powell. The original operating plan called for 7.48 million acre-feet to leave Powell during the water year. As conditions deteriorated, that release was reduced to 6 million acre-feet. In practical terms, the government was working on both sides of the reservoir at once. More water would be directed toward Powell from upstream. Less water would be allowed to leave Powell downstream. On their own, those actions could be described as separate adjustments. Together, they describe something larger. The system was closing around Lake Powell, trying to hold its elevation above a level where ordinary dam operations become much more difficult. Then another signal appeared. According to the Bureau of Reclamation, the April probable minimum forecast placed Lake Powell inflow for the water year at 2.78 million acre-feet, only 29% of the historical average. The same federal modeling showed that, without major intervention, the reservoir could fall below 3,490 feet above sea level by August. That number matters because 3,490 feet is not simply another mark painted on a canyon wall. It is the minimum power pool at Glen Canyon Dam, the elevation below which water can no longer enter the penstocks that feed the hydroelectric turbines in the normal way. So by the time the Flaming Gorge releases began, operators were not responding to one bad forecast. They were responding to a configuration. Weak inflow was approaching from upstream. A critical elevation was approaching from below. Water deliveries still had to continue downstream. Power production depended on enough water remaining above the turbine intakes. And every choice made at one reservoir changed the margin available at another. This is what the operational dashboard looked like. At Flaming Gorge, reservoir releases increased and began moving into the Green River. At Lake Powell, monthly releases through Glen Canyon Dam were being reduced to retain more storage. In federal forecasting offices, the 24-month study was being updated as snow conditions, runoff, reservoir levels, and scheduled releases changed. In power operations, planners were watching the hydraulic head. the vertical pressure created by the height of water above the turbines. In the upper basin states, water managers were tracking how much protection could be transferred toward Powell without creating unacceptable damage elsewhere. And downstream, users could not simply pause their dependence on the river while the reservoirs recovered. The river was still expected to support cities, farms, tribal communities, ecosystems, recreation, and electricity generation across a vast region. This is why the date matters. April is normally when attention begins turning toward the spring runoff, the period when melting mountain snow sends a large share of the year's water into the Colorado River system. In an ordinary year, managers would be watching the reservoirs respond to that incoming pulse. In this year, they were preparing emergency operations before the full runoff season had resolved the picture. The system was not waiting to see whether the problem would become visible from the shoreline. It was acting because the forecasts showed where the shoreline might be months later. But there was an even stranger detail in the data. Flaming Gorge itself was not receiving abundant water. By early July, the reservoir stood at about 75% of its active storage capacity. Its unregulated inflow during June was only about 31% of average. Federal projections for July, August, and September also remained far below average. In other words, the reservoir being asked to help Lake Powell was facing weak inflow of its own. This was not a full bucket rescuing an empty one. It was one reserve account transferring part of its balance to protect another reserve account from crossing a more immediate operational threshold. That distinction changes the entire story. If heavy snow or exceptional runoff were filling Flaming Gorge faster than expected, sending water south could be described as distributing a temporary surplus. That is not the configuration on the board. The additional release is a deliberate draw on stored water, made because the risks at Powell are considered more urgent. And once that water leaves Flaming Gorge, operators cannot summon it back by reversing a valve. It enters a long river corridor. It affects flows, temperatures, habitats, recreation, and dam schedules along the way. It eventually reaches Lake Powell only after moving through the connected geography of the upper Colorado River basin. The map shows water traveling south. But the operational system shows risk being redistributed. That is the first major turn in this story. The emergency action may improve the elevation at Powell while reducing the cushion available at Flaming Gorge. It may protect power generation at Glen Canyon while changing generation and storage conditions upstream. It may preserve the ability to release water through one dam while asking another reservoir to carry less protection into the next dry period. None of this means the action is unnecessary. The federal plan exists because allowing Powell to cross a critical threshold could produce consequences that spread far beyond the reservoir itself. But it does mean the word emergency must be understood correctly. Emergency water is not new water. It is water taken from somewhere else in the system and assigned to the place where failure appears closest. By late spring, the federal dashboard therefore contained at least 4 connected alarms. Lake Powell's minimum probable inflow was dramatically below average. The projected elevation threatened minimum power pool. Glen Canyon Dam releases had been cut to retain nearly 1.5 million acre-feet more than originally planned, and Flaming Gorge had begun supplying an additional volume that could reach 1 million acre-feet. The combined effect could raise Powell by many feet compared with the path it would follow without those actions. But even that improvement would not mean the drought had ended or the basin had recovered. It would mean the operators had altered the path of decline. Picture the control room not as a place where someone presses a button and solves the crisis, but as a place where every available button has a cost. Increase the release from Flaming Gorge, and its storage falls faster. Reduce the release from Powell, and less water reaches Lake Mead during that period. Protect hydropower elevation, and another part of the system must absorb the adjustment. Follow the probable minimum forecast, and the need for intervention becomes urgent. Follow a wetter forecast, and some emergency actions may appear larger than necessary. Operators must act before they know exactly which future will arrive. That uncertainty is not a flaw in the forecast. It is the condition under which reservoir management works. Decisions made now shape elevations months later, after snow has melted. Water has traveled hundreds of miles, and demand has continued across the basin. This is why the signals cannot be separated. The release from Flaming Gorge, the reduced outflow at Glen Canyon, the weak inflow forecast, and the minimum power pool threshold are all parts of the same configuration. The river is being managed not only for the water available today, but for the elevation that may remain at the end of summer and the infrastructure that must still function after that. The unusual feature is not simply that Lake Powell is low, it is that federal operators are using upstream storage and downstream restraint at the same time to defend a narrow operating margin. The water moving through the Green River is visible. The decision behind it is less visible. And the most important number is still ahead, because to understand whether this intervention is large enough, we must first understand what 1 million acre-feet actually means inside a reservoir the size of Lake Powell. The number is 1 million acre-feet. It is large enough to dominate the announcement, large enough to change Lake Powell's projected elevation, and large enough to sound like an answer. But before that number can explain the emergency, it has to be pulled apart. An acre-foot is the amount of water required to cover 1 acre of land to a depth of 1 foot. It equals approximately 325,851 gallons. Multiply that by 1 million, and the maximum planned contribution from Flaming Gorge becomes nearly 326 billion gallons of water. Imagine a square pool covering 1 million acres, an area larger than the state of Rhode Island, with water standing 1 foot deep across every road, field, building, and hillside. Or imagine enough water to fill almost 500,000 Olympic-sized swimming pools. Those comparisons help the mind feel the scale. They also create a trap. 326 billion gallons sounds almost limitless when viewed outside the Colorado River system. Inside that system, it is a temporary operating tool. Lake Powell has a total storage capacity of about 25.16 million acre-feet. At full capacity, the maximum Flaming Gorge contribution would equal roughly 4% of the water Powell was designed to hold. That is not small. 4% of one of the largest reservoirs in the United States is an immense physical volume, but it is not restoration. It does not refill the canyon. It does not erase years of declining storage. And it does not guarantee that the next runoff season will replace what has been spent. The number is not just water, it is time being transferred from one reservoir to another. The federal plan does not promise that exactly 1 million acre-feet will be released. It establishes a range from approximately 660,000 acre-feet to 1 million acre-feet of additional water through April of next year. At the lower end, that is about 215 billion gallons. At the upper end, it is nearly 326 billion. The difference between those two limits is 340,000 acre-feet, more than 110 billion gallons. That range exists because reservoir operations cannot be fixed months in advance, as if the river were a conveyor belt. Snowpack changes, runoff forecasts change, summer temperatures alter demand and evaporation, tributaries add water, dry soils absorb it, scheduled releases are adjusted, environmental flow requirements must be considered. The final volume depends on what the basin does while the operation is underway. This is the first reason the headline number must be treated carefully. 1 million acre-feet is a ceiling within an operating plan, not a single block of water already sitting inside Lake Powell. The water is delivered over time. It leaves Flaming Gorge through controlled releases, enters the Green River, moves downstream, and eventually joins the Colorado River before reaching Powell. The journey extends roughly 455 river miles. The release measured at Flaming Gorge is therefore not experienced at Lake Powell as one sudden arrival. It becomes a stretched pulse, moving through a living river system. Some days carry more of it, some days carry less. Natural inflows mix with it. River conditions change around it. By the time the operation becomes visible in Powell's elevation, the water has already been traveling for days, and the reservoir has continued gaining and losing water from other sources. That makes attribution difficult for anyone watching only the shoreline. Powell may rise during part of the operation, but not every inch of that rise comes from Flaming Gorge. Powell may also fall while the additional water is arriving if releases, evaporation, and other losses exceed total inflow. The correct question is not simply whether the lake rises. It is how much lower the lake would have been without the intervention. That is a different measurement. It compares the reservoir with an alternate path that did not occur. Federal models must estimate that path using forecasts, scheduled releases, hydrology, and reservoir geometry. This is why officials often describe the operation in terms of protection rather than recovery. The water changes the projected trajectory. It does not remove the forces pushing the reservoir downward. A useful precedent shows how elevation responds to volume. During earlier drought operations, a combined change of approximately 1 million acre-feet, created through supplemental upstream releases and water retained at Powell, was estimated to add roughly 16 feet to the reservoir's elevation, compared with the path it otherwise would have followed. 16 feet sounds dramatic. It can be the difference between remaining above an operating threshold and crossing it. But 16 feet at Lake Powell does not mean the reservoir has recovered 16 feet of lost security forever. Reservoir elevation is not a savings account with identical steps. The canyon is irregular. Its walls widen and narrow. At some elevations, raising the surface by 1 foot requires more water than at others because the surface spreads over a larger area. At lower levels, submerged benches, side canyons, and the shape of the main channel change the relationship between volume and height. The same acre-foot can therefore produce a different elevation response depending on where the reservoir begins. The number is not just volume, it is volume entering a changing container. This is also why photographs can mislead. A person standing at an overlook may see a visible band of pale rock hundreds of feet high and conclude that 1 million acre-feet cannot matter. From that perspective, the operation looks tiny. A power system operator sees something different. A rise of several feet near a critical threshold can protect hydraulic head, maintain access to turbine intakes, and preserve options for moving water through the dam. The public sees an enormous reservoir that remains far below full. The control room sees distance above a specific elevation. Both views are accurate. They are measuring different forms of risk. Yet the scale becomes even more complicated when the source reservoir is included. When drought response releases began, Flaming Gorge held approximately 3.01 million acre-feet and was about 82% full. A maximum additional release of 1 million acre-feet would be equal to roughly 1/3 of that initial stored volume. That does not mean Flaming Gorge will simply lose 1/3 of its water, because inflows continue and normal releases would have occurred even without the emergency plan. The federal figure refers to additional water above the operating path that would otherwise have been followed. Still, the comparison reveals the weight of the decision. 1 million acre-feet is only about 4% of Lake Powell's total capacity, but it is a much larger share of the water held in Flaming Gorge. The same number looks modest at the receiving reservoir and enormous at the supplying reservoir. This is not a contradiction. It is the geometry of moving protection through a system of unequal containers. The headline focuses on what Powell gains. The fuller calculation includes what Flaming Gorge gives up. Then there is the second part of the federal intervention. Water is not only being added from upstream, more water is also being retained at Powell. The annual release from Glen Canyon Dam was reduced from 7.48 million acre-feet to 6 million acre-feet, a difference of 1.48 million acre-feet. That retained volume is almost 50% larger than the maximum planned contribution from Flaming Gorge. Put the two actions together at their upper limits, and the operational change around Powell reaches approximately 2.48 million acre-feet compared with the earlier release plan, and a scenario without the additional upstream water. That is more than 800 billion gallons. But even this combined number should not be mistaken for new supply. The retained water is water that does not move downstream during the same period. The transferred water is storage removed from another reservoir. The system is improving Powell's position by changing where existing water is held and when it is released. No storm created the 2.48 million acre-feet. No new snowpack appeared when the operating order was signed. The basin did not become wetter. Its managers rearranged the remaining margin. This is the central abnormality hidden inside the impressive number. In an ordinary recovery, a reservoir rises because runoff brings additional water into the system. In this operation, Powell can improve because water is being concentrated there. One reservoir releases more, another releases less. The receiving lake gains elevation, but total basin storage does not gain the same amount. It may continue declining despite the local improvement. This is not just a reservoir release. This is a system buying time with water it cannot replace. How much time does 1 million acre-feet purchase? There is no single answer. If inflow remains extremely weak, the water may offset only part of the decline. If runoff improves, the same intervention may preserve a wider safety margin. If another dry year follows, the water removed from Flaming Gorge may be missed upstream just as urgently as it is needed at Powell today. The value of the release is therefore determined not only by its size, but by what happens after it arrives. 1 billion gallons can sound permanent. In a river serving tens of millions of people and millions of acres of agriculture, it moves quickly into obligations, losses, power generation, environmental flows, and the next operating decision. The headline number is enormous enough to matter. It is not enormous enough to stand alone. And once the scale is understood, the next question becomes unavoidable. If 1 million acre-feet is the visible rescue, what hidden number tells operators whether the rescue has actually kept Glen Canyon Dam functioning? The visible number is 1 million acre-feet. The hidden number is 35 feet. That is the operating buffer between Lake Powell's target elevation of 3,525 feet and minimum power pool at 3,490 feet. On a reservoir that once rose hundreds of feet behind Glen Canyon Dam, 35 feet can sound minor. It is not minor. It is the distance between a dam operating largely as designed and a dam entering a narrower, more difficult operating condition. This is where the story changes. Water volume makes the headline. Elevation writes the damage. To understand why, imagine two containers holding the same amount of water. One is tall and narrow. The other is broad and shallow. The water volume may be identical, but the height of the water above an opening near the bottom can be very different. Lake Powell is vastly more complex than either container. It fills a branching canyon system where the relationship between storage and elevation changes at every level. As the reservoir falls, the important question is no longer only how many acre-feet remain. The question is where the surface sits in relation to the structures that allow Glen Canyon Dam to generate electricity and release water downstream. At full pool, Lake Powell's surface is near 3,700 feet above sea level. The federal drought response target is 3,525 feet. Minimum power pool is 3,490 feet. Dead pool is near 3,370 feet. These are not four versions of the same warning. Each elevation represents a different physical and operational condition. At 3,525 feet, operators have a 35-foot cushion above minimum power pool. That cushion provides room for forecast error, changing inflow, evaporation, monthly releases, and the possibility that dry conditions continue longer than expected. At 3,490 feet, the reservoir reaches the lowest elevation at which Glen Canyon Dam can currently generate hydropower through its turbines. Below that point, the dam's ability to release water is reduced. Ordinary power generation stops, and operators must depend more heavily on other outlet structures. At approximately 3,370 feet, the reservoir reaches dead pool, the level at which water can no longer flow through the dam in excess of what enters the reservoir. The lake may still contain water, but gravity can no longer move that stored water through the available outlets in the normal way. This is the hidden logic of the emergency. A reservoir does not have to become empty before it loses functions. It can hold billions of gallons and still become less capable of delivering them. The public tends to imagine reservoir danger as an empty basin. Engineers watch something more precise. They watch the shrinking vertical distance between the water surface and a series of openings built into concrete. That distance affects whether water can reach the turbines, how much pressure pushes it through the penstocks, how efficiently electricity can be generated, and which release routes remain available. The event is visible on the shoreline. The damage begins at the intake. Hydroelectric power at Glen Canyon Dam depends on hydraulic head. Hydraulic head is the force created by the height of water above the turbines. When the reservoir is high, a tall column of water presses downward and drives the turbines with greater force. As the surface falls, that column becomes shorter. The pressure decreases. The same machinery operates with less available energy. Power generation can decline before the reservoir reaches minimum power pool because every foot lost reduces part of the hydraulic advantage. Then, at the threshold itself, the problem becomes geometric. The turbine intakes cannot function normally when the surface drops too close to their operating range. The hidden number is therefore not merely the elevation on a particular day. It is the remaining margin above a physical limit. This is why a forecast of 3,490 feet changes federal behavior months before the water arrives there. Reservoir operations move slowly. Water released from Flaming Gorge must travel hundreds of river miles. Snowmelt arrives according to temperature, soil conditions, and mountain hydrology, not according to the urgency of a federal meeting. Water retained at Powell today changes conditions later in the year. By the time the critical elevation is visible at the dam, the decisions capable of preventing it may already be far behind. Operators must respond to projected margin, not wait for physical failure. According to the Bureau of Reclamation, the April minimum probable projection showed Lake Powell falling below minimum power pool by August without major intervention. That statement does not mean the reservoir was certain to cross the threshold. A minimum probable forecast is a dry scenario within a range of possible outcomes. Weather could improve. Runoff could exceed the projection. Demand or releases could change. But the forecast mattered because the consequence was too serious to treat as a distant possibility. When a dam supports downstream water movement, regional hydropower, environmental programs, and interstate obligations, a credible projection of reduced functionality becomes an operational signal. The warning does not wait for certainty. It waits for risk to become large enough that delay carries a greater cost than action. This also explains the importance of the target elevation at 3,525 feet. The target is not minimum power pool itself. It is 35 feet above it. That separation is deliberate. A system that protects only the exact failure line is not protected. Forecasts contain uncertainty. Inflows can weaken. Temperatures can increase evaporation and water demand. A reservoir can lose elevation faster than expected during a hot, dry period. Scheduled releases cannot always be stopped without affecting users and obligations downstream. The 35-foot target is an attempt to preserve room for those errors and pressures. It is the equivalent of maintaining braking distance rather than planning to stop with the front wheels at the edge of a cliff. But here is the uncomfortable part. A 35-foot buffer is not a fixed quantity of water. Because the reservoir changes shape with elevation, the volume contained within those 35 feet depends on where the water spreads through the canyon. As Powell falls, each foot on the gauge carries its own storage value. This makes the relationship between the million-acre feet coming from Flaming Gorge and the 35-foot buffer more complicated than simple division. The additional water may add several feet, or help prevent several feet of decline, depending on inflow, outflow, evaporation, and the starting elevation. It can be decisive without being sufficient. If the reservoir would otherwise fall just below minimum power pool, a few protected feet may preserve hydropower and ordinary release capacity. If the hydrology deteriorates more sharply, the same volume may slow the approach without stopping it. The headline asks, how much water is coming? The control room asks how much elevation remains after everything else happens. And everything else is still happening. Water continues to leave Powell through Glen Canyon Dam, even after annual releases were reduced. The reservoir continues losing water to evaporation. Natural inflow continues arriving, but at levels far below average under the driest forecasts. Tributaries rise and fall. Summer heat changes demand. The flaming Gorge pulse moves downstream over time rather than arriving as one clean block. Every one of those processes changes the final elevation. This means the hidden number is dynamic. It can widen after a strong runoff period and narrow again through the summer. It can look comfortable under the most probable forecast and dangerous under the minimum probable forecast. It can improve locally at Lake Powell, while storage protection weakens elsewhere in the upper basin. A single number on a dashboard therefore carries an entire chain of assumptions behind it. The danger is not that officials do not know the exact future. The danger is that the dam has physical thresholds, even when the future remains uncertain. The machinery does not adjust its intake elevation because the snow forecast was difficult. Concrete does not negotiate with drought. Once the water surface reaches a physical limit, operational options change, whether the decline was predicted perfectly or not. This is why minimum power pool is more than a hydropower problem. Glen Canyon Dam was designed as a multi-purpose structure within the Colorado River storage project. Its turbines generate electricity, but the reservoir also helps regulate water moving from the upper basin toward the lower basin. Hydropower revenues support the operation and maintenance of federal facilities and contribute to environmental and recovery programs across the region. If power generation stops, the immediate electricity loss is only the first visible effect. Replacement power must come from somewhere else. It may cost more. Revenue streams can weaken. Dam operations become less flexible. Downstream releases may depend more heavily on outlet works that were not intended to replace the turbines as the normal long-term pathway. The weak point is a set of intakes, but the consequences spread through institutions, contracts, budgets, ecosystems, and the electrical grid. There is another distinction that matters. Minimum power pool is not dead pool. Crossing 3,490 feet would not mean the Colorado River instantly stops below Glen Canyon Dam. Other outlet structures can pass water at lower elevations, but their capacity and performance are not identical to the turbines, and very low reservoir levels create engineering questions that do not exist under normal conditions. Water passing through lower outlets can behave differently. Pressure, vibration, air entrainment, cavitation, and sediment all become more important as operators move away from the conditions for which the system was routinely used. The evidence does not support saying the dam would immediately fail. It supports saying that the operating envelope would become smaller, less familiar, and less forgiving. That is serious enough. The hidden number is not a cinematic countdown to an empty lake. It is a measure of lost options. At higher elevations, operators can release water through turbines, produce power, adjust schedules, and absorb forecast errors with a larger storage cushion. As elevation falls, each option narrows. First, power efficiency weakens. Then, power production becomes threatened. Then release capacity may become more constrained. Finally, at dead pool, stored water loses the ability to pass the dam by gravity beyond incoming flow. The progression is not one sudden collapse. It is a staircase of reduced functionality. The emergency releases are designed to keep the system from stepping down that staircase. But every foot protected at Powell comes from decisions elsewhere. Flaming Gorge is giving up part of its stored cushion. Glen Canyon Dam is releasing less than previously scheduled. Lake Mead receives less water during the same period than it would have under the original plan. The Colorado River Basin is not eliminating risk. It is positioning water around the most immediate weak point. That is the central revelation. The visible number makes the intervention look like a rescue measured in gallons. The hidden number reveals that the intervention is really a defense measured in feet. 1 million acre-feet matters because of where it may hold the surface relative to steel intakes embedded in a concrete dam. 35 feet matters because it separates a target operating condition from the loss of normal hydropower. And the next threshold matters because a reservoir can remain enormous while the infrastructure around it becomes progressively less useful. Powell may rise, the basin may remain dry, the dam may keep operating. The margin may continue shrinking. To understand how all of these statements can be true at the same time, we have to follow the mechanism that carries snowmelt, stored water, pressure, electricity, and risk through the system. The mechanism begins hundreds of miles above Lake Powell, where winter precipitation accumulates in the mountains as snow. That snow is the first reservoir in the system, even though it has no concrete walls and no control gates. During winter, it stores water in place. During spring, rising temperatures begin releasing that storage into soil, small channels, tributaries, and eventually the Colorado River network. In a healthy water year, this process creates a long pulse of runoff that fills streams and raises reservoirs. But snow depth alone does not determine how much water reaches a dam. Before runoff can enter a river, it must cross the ground, and the ground can take part of it. After a hot or dry year, mountain soils may begin spring with a large moisture deficit. The first snowmelt does not immediately become streamflow. It enters pores in the soil, wets roots, feeds vegetation, and replaces water lost during the previous season. Some returns to the atmosphere through evaporation. Some is pulled through plants and released through their leaves. Only the remaining portion becomes runoff. This is why a snowpack that appears close to average can produce a river flow far below average. The snow is visible. The missing runoff is hidden in the soil and atmosphere. The mechanism is called runoff efficiency. In simple terms, runoff efficiency describes how much precipitation eventually becomes water moving through the river. When soils are wet and temperatures remain cool, a larger share can reach streams. When soils are dry and spring warms rapidly, more water is absorbed or returned to the air before it reaches a gauge. The river does not receive the amount that fell from the sky. It receives what survives the journey. That difference is one reason the Colorado River system can enter spring with snow in the mountains and still face an emergency forecast at Lake Powell. The map shows snow, the reservoir receives runoff. Those are not the same measurement. Once water reaches a mountain stream, gravity begins carrying it through a branching network. Small flows combine into larger tributaries. Tributaries enter the Green River and the Colorado River. Dams interrupt that movement, holding part of the water behind concrete and releasing it according to operating plans. Flaming Gorge Dam is one of those control points. It captures water behind a structure rising more than 500 feet above the riverbed and forms a reservoir extending north into Wyoming. Under ordinary operations, managers balance storage, hydropower, downstream habitat, recreation, flood control considerations, and water delivery requirements. During drought response operations, another purpose moves to the front. Flaming Gorge becomes a source of elevation protection for Lake Powell. That does not mean a separate pipe connects the two reservoirs. The river itself becomes the delivery system. Operators increase releases through Flaming Gorge Dam. The water enters the Green River and begins a journey of roughly 455 river miles. It passes through a landscape of canyons, tributaries, wetlands, diversion points, temperature changes, and ecological constraints. It does not travel as a labeled parcel. No boundary separates emergency water from ordinary river water. Instead, gauges measure flows before and after the operational change. Models estimate how much additional water the release contributes to downstream conditions. The signal moves through the river as a managed increase layered onto natural flow. This is the first transformation. Stored water becomes river flow. At the dam, water has elevation and pressure. Below the dam, it has velocity, timing, temperature, and ecological force. A larger release can raise the river stage. It can alter conditions for fish, boaters, shoreline vegetation, and communities using the Green River corridor. Operators cannot treat the channel as an empty pipe because the channel is also habitat and infrastructure. Releases must therefore be shaped over time. The target volume may be enormous, but it is delivered through daily and monthly decisions. 1 million acre-feet cannot be sent south in one uncontrolled surge. The river could not safely carry it. Downstream ecosystems could be damaged, and the supplying reservoir would fall too rapidly. The volume has to be translated into a release schedule. That schedule is the mechanism's heartbeat. At every adjustment, operators compare the amount leaving Flaming Gorge with the reservoir elevation, expected inflow, downstream flow limits, and Lake Powell's projected need. If forecasts improve, the operation can be modified. If conditions worsen, the release may move toward the upper end of the planned range. The plan is therefore not one decision made in April. It is a sequence of decisions extending through the following year. By the time the additional water reaches Lake Powell, it has joined natural runoff and other tributary flows. There, the mechanism changes again. River flow becomes reservoir storage. As water enters the upper reaches of Powell, its forward motion slows. Sediment begins settling. The water spreads into the long flooded canyons behind Glen Canyon Dam. Its effect is no longer measured primarily in cubic feet per second. It is measured in acre-feet of storage and feet of reservoir elevation. But incoming water does not simply stack on top of the lake and remain there. Powell is a balance sheet in motion. Water enters from the Colorado, Green, San Juan, and smaller tributaries. Water leaves through Glen Canyon Dam. Water evaporates from the reservoir surface. Banks and sediments exchange moisture with the lake. The elevation at any moment is the physical result of all those additions and subtractions. This is why emergency water can arrive while the reservoir continues falling. If total outflow and losses remain greater than total inflow, Powell declines more slowly than it would have without the release, but it still declines. The rescue may appear as a fall that did not happen rather than a rise that everyone can see. That is difficult to photograph. It is not difficult to model. Federal operators compare possible trajectories. One line represents conditions with the additional water and reduced releases. Another represents what could happen without those actions. The vertical distance between those lines is the protection purchased by the intervention. This is not a restoration mechanism. It is a trajectory-changing mechanism. Then the stored water reaches the next physical stage. At Glen Canyon Dam, elevation becomes pressure. The water surface stands hundreds of feet above the turbines. That vertical distance creates hydraulic head. The taller the column of water, the more gravitational energy it contains. Water enters intake structures, accelerates through large penstocks, and pushes against turbine blades. The turbines rotate generators. The generators convert mechanical motion into electricity. After passing through the machinery, the water returns to the Colorado River below the dam and continues toward the Grand Canyon and Lake Mead. In this way, the same water performs several jobs in sequence. It supports reservoir elevation. It creates pressure. It generates electricity. It becomes a downstream release. It helps maintain river flows required by a larger operating system. But the process depends on position. Water stored too low behind the dam cannot perform all of those jobs in the same way. As Powell falls, hydraulic head declines. Each unit of water reaches the turbines with less pressure than it would have at a higher elevation. The generators can still operate, but available capacity and efficiency weaken. When the surface approaches minimum power pool at 3,490 feet, the geometry becomes critical. The reservoir may still contain a vast amount of water, but the ordinary turbine pathway is no longer reliably available below that threshold. The hidden mechanism is not disappearance. It is loss of access. Imagine a drinking glass with a straw fixed through its side. The glass can still hold water below the straw, but that remaining water cannot exit through the straw. Glen Canyon Dam is vastly more complex, and it has additional outlet structures, but the basic relationship is similar. Storage below an intake is not operationally equal to storage above it. This is why managers are defending elevation, rather than waiting for Powell to become empty. The infrastructure does not use every gallon in the reservoir equally. Its usefulness depends on where that gallon sits relative to steel, concrete, pressure, and gravity. Once electricity is generated, the mechanism moves beyond the river. Power from Glen Canyon Dam enters the regional electrical system and is marketed to customers across the West. Hydropower is valuable not only because it produces energy, but because operators can adjust it relatively quickly as demand changes. When people turn on air conditioners during a hot afternoon, when solar output drops near sunset, or when another generator unexpectedly goes offline, flexible hydropower can help the grid respond. Lower reservoir elevations reduce that flexibility. Less hydraulic head can mean less generating capacity. Crossing minimum power pool would remove normal hydropower production at the dam altogether. Replacement electricity would have to come from other sources. Those sources may be more expensive, may produce more emissions, or may already be needed during periods of high demand. The water crisis, therefore, enters the grid through a turbine. It also enters public budgets. Revenue from Colorado River Storage Project. Power supports facility operation, maintenance, and federal programs connected to endangered species recovery and salinity control. When hydropower generation declines, the effect is not confined to a meter at the power plant. It can weaken the financial structure, supporting work across the basin. Water becomes pressure. Pressure becomes electricity. Electricity becomes revenue. Revenue becomes maintenance and environmental programs. A falling reservoir can move through that entire chain, but there is another direction to follow. The mechanism also travels backward toward Flaming Gorge. Every additional acre-foot released south is an acre-foot no longer stored in the supplying reservoir. Future inflow may replace part of it. A wet year may restore much of the lost storage. A dry year may not. The operation therefore exchanges one form of uncertainty for another. Powell receives a larger immediate buffer above critical infrastructure. Flaming Gorge carries a smaller buffer against future drought, weak runoff, ecological demands, and local economic effects. This is not an accidental side effect. It is the basic logic of drought response operations. Water is moved from a reservoir, with more available operating space, toward a reservoir facing a more urgent threshold. The system protects the point closest to losing function. But that protection cannot be repeated indefinitely unless nature replenishes the source. A reservoir release can move stored water. It cannot manufacture runoff. A dam can change timing. It cannot change the total precipitation that survived. Dry soil, warm air, vegetation, and evaporation. This is where the mechanism returns to the mountains. If future snowmelt produces strong inflow, the system can rebuild part of what it spent. If runoff efficiency remains poor, storage recovery becomes slower, even when snow appears respectable. The emergency release then becomes more than a temporary transfer. It becomes another withdrawal from a reserve that may take years to replace. By the time the mechanism becomes visible as a lower boat ramp at Flaming Gorge, a higher shoreline at Powell, reduced power output at Glen Canyon, or a change in a downstream flow schedule, the system has already been carrying the load for months. It began in winter precipitation. It passed through spring temperature and dry soil. It entered tributaries, dams, operating plans, river channels, reservoir geometry, turbine intakes, generators, power contracts, and public programs. The water did not simply move south, risk moved with it. And the next part of the story is not found on a federal chart. It is found in the life of someone whose work, electricity, income, or next decision depends on where that water ends up. The body does not experience a reservoir crisis as a graph. It experiences it as a decision that arrives at the wrong time. Consider a farmer in the upper Colorado River Basin at the beginning of another dry summer. He wakes before sunrise because the day will become too hot to work safely by afternoon. Before he checks the weather, he checks water. The irrigation schedule on his phone tells him when a limited amount will move through the local canal. The electricity rate tells him how much it will cost to run the pump. The condition of his field tells him whether the last application reached the root zone or disappeared into dry soil. None of these measurements carries the name Flaming Gorge or Lake Powell. Yet the same mechanism is moving through all of them. Outside, the river system is losing flexibility. Inside the farm office, that loss becomes a narrower set of choices. He can irrigate early and hope the water lasts. He can delay and risk heat stress during a critical stage of crop growth. He can pump more groundwater if the well and permit allow it, but that adds electricity costs and may lower the water table. He can reduce acreage, buy feed instead of growing it, sell animals earlier than planned, or carry another season of debt. The river does not enter his life as a single disaster. It enters as a sequence of compromises. The first pathway begins in the soil. When irrigation water reaches a dry field, part of it must replace moisture already missing from the ground before plants receive what they need. The farmer sees water entering the furrow, but he cannot assume that the crop receives all of it. Hot air increases evaporation. Dry wind pulls moisture from leaves. Compacted or crusted soil may reduce infiltration in one area and increase runoff in another. A damaged canal can lose water before it reaches the field. The headline volume exists at the reservoir. The useful volume is what reaches the root. That difference is the human version of runoff efficiency. At the basin scale, snowmelt is reduced as it crosses dry soil and warm air. At the farm scale, delivered water is reduced as it crosses a canal, a ditch, a pump, and a thirsty field. In both cases, the system can report water moving, while the person at the end receives less benefit than the number suggests. Now follow the same pathway into the body. The farmer steps out before dawn. But the night has not cooled enough. His body begins work without fully releasing the heat stored from the previous day. Sweat starts earlier. Heart rate rises. Water loss accelerates. The job requires attention because a blocked gate, a failed pump, or a broken line can waste part of an already limited irrigation turn. Yet dehydration narrows concentration and slows reaction time. A mistake made during a normal year may cost labor. A mistake made during a restricted delivery can cost the only reliable watering window available that week. The body does not experience drought as a percentage of average. It experiences thirst, fatigue, dizziness, muscle cramps, and the pressure to keep working because the water will not wait. If he stops, the irrigation turn continues moving past his field. If he works through the symptoms, the medical risk grows. This is where climate, infrastructure, and labor meet. The canal follows a schedule. The crop follows a biological clock. The body follows limits of heat and hydration. None of those clocks can be reset simply because the reservoir system is under stress. Then the mechanism reaches income. A crop underwatered during a critical growth stage may produce less, mature unevenly, or fail to meet market quality. Livestock exposed to heat require more water while eating less. Pasture growth weakens. Feed prices rise when dry conditions affect many producers at once. The farmer may spend more money to produce less. That difference travels into a loan payment, an equipment repair, a school bill, or a decision to postpone medical care. Drought does not stay in the river because money does not stay on the farm. A reduced harvest changes work for truck drivers, processors, equipment dealers, veterinarians, local stores, and seasonal laborers. 1 acre-foot moved between reservoirs may seem far removed from a household budget, but the larger operating shortage that made the transfer necessary is already passing through prices and decisions across the basin. This does not mean the Flaming Gorge release directly determines whether one farm succeeds or fails. That would be a false causal claim. Individual farms depend on local water rights, contracts, weather, crop choice, soil, debt, and many other conditions. The connection is systemic, not mechanical in the narrow sense. Emergency releases reveal that the basin has less reserve available to absorb future shocks. Less reserve means less confidence. Less confidence changes planning. A farmer who believes water will be available can invest in seed, labor, and equipment. A farmer who expects shortage may reduce acreage before the first field dries. The physical drought enters the economy through expectation. That is the detail people often miss. Damage begins before a canal runs empty. It begins when uncertainty becomes expensive. The same water crisis can enter a different life through electricity. Imagine a family living in a small desert town downstream, where summer temperatures remain high after sunset. Their home is cooled by an aging air conditioner. Their monthly budget has little room for a higher power bill. Glen Canyon Dam does not supply every electron reaching that house, and a decline in hydropower does not automatically cause a local blackout. But reduced hydropower can remove a flexible and relatively low-cost source from the regional system. Utilities may need replacement electricity from other generators or markets. During periods of extreme demand, that replacement can be more expensive. The system-level adjustment eventually appears in rates, surcharges, public budgets, or reduced room for other investments. The family experiences the river as a thermostat decision. Set the temperature lower and the bill rises. Set it higher and sleep becomes difficult. A child wakes repeatedly. An older adult with heart or respiratory disease carries greater heat stress. Medication may affect hydration. A window can be opened, but wildfire smoke or hot nighttime air may make that option unsafe. The body does not experience hydropower loss as a megawatt figure. It experiences a room that fails to cool. Follow the pathway one step further. Poor sleep reduces concentration the next day. A worker driving to an early shift reacts more slowly. A child struggles in school. An older adult becomes less able to regulate body temperature after several hot nights. The household may avoid using the air conditioner during the most expensive hours, exactly when outdoor heat is highest. If the unit fails, repair costs compete with food, rent, and medicine. The weather is outside. The load accumulates inside. The connection to Lake Powell remains indirect, but it is real. A lower reservoir means less hydraulic head. Less head means reduced generating capability. Reduced capability means less flexible power available to the grid. The grid compensates through other resources. Those resources carry costs and limits. Eventually, some part of that adjustment reaches a person who has never seen Glen Canyon Dam. There is also a worker inside the dam whose day is shaped by the shrinking elevation margin. He enters a facility built to make enormous forces appear controlled. Displays show reservoir elevation, release rates, turbine condition, vibration, pressure, and electrical output. Under ordinary conditions, the numbers move within familiar ranges. As the reservoir falls, the same controls must operate with less hydraulic head. The turbines still turn, but performance changes. Maintenance decisions become more important because the system has less margin for equipment to be unavailable. A planned outage that once appeared routine can become more difficult to schedule when every operating unit matters. The worker does not experience drought as a dry field. He experiences it as a narrowing envelope on a screen. A reading that would once have been unremarkable now sits closer to a limit. A forecast update changes, staffing, maintenance planning, and the assumptions used for the next month. The pressure is psychological as well as mechanical. Every decision has consequences beyond the power plant. Increase a release and Powell loses elevation faster. Reduce it and downstream conditions change. Shut down a unit for maintenance and generation falls. Delay maintenance and equipment risk can increase. The weak point outside becomes a burden inside the control room. Then the mechanism enters a tribal community whose relationship with the river is older than the dams. The Colorado River system supports drinking water, agriculture, cultural practices, ecosystems, and economic development across tribal lands. Yet access to infrastructure is uneven. Some households still face unreliable water service or must haul water over long distances. A regional reservoir operation may involve millions of acre-feet, while a family measures security in containers carried home. This contrast is not rhetorical. It reveals how system scale can hide human scale. A policy can protect an elevation at Lake Powell and still leave communities without the pipes, treatment systems, or legal certainty needed to benefit fully from the river. Water can exist in the basin and remain inaccessible to the person who needs it. Again, the hidden number is not only volume, it is access. The same drought response action can therefore produce different human meanings. For a federal operator, the release is a tool to protect infrastructure. For a farmer near the Green River, it may mean higher flows passing the property today, but less stored cushion upstream tomorrow. For a recreation business at Flaming Gorge, a lower reservoir may affect ramps, shorelines, visitor patterns, and revenue. For a power customer, reduced hydropower may become a financial pressure rather than a visible water shortage. For an ecosystem manager, release timing may alter temperature and habitat. For a household hauling water, the scale of federal storage may feel disconnected from daily scarcity. The river is one system. The pathways through people are unequal. That inequality matters because resilience depends on who has alternatives. A large farm may change crops, purchase additional water, or absorb one bad season. A small producer may not. A wealthier household can replace an air conditioner or pay a higher bill. A low-income household may endure unsafe indoor heat. A utility with diverse generating sources can replace hydropower more easily than a customer can replace income. A community with modern treatment and storage can tolerate short disruptions. A household without reliable service begins with no cushion at all. The emergency operation is designed around reservoir margins, but human safety is also a question of margin. How many days of savings remain? How many hours of sleep are lost? How much groundwater can be pumped? How much heat the body can carry? How much uncertainty a business can finance? This is why the phrase buying time is more than a metaphor. The system is literally purchasing time above a physical threshold by spending stored water elsewhere. But time has different value depending on who receives it. At Lake Powell, a few additional feet may preserve turbine operations. At a farm, a few additional days of reliable delivery may preserve a crop. In a home, a few hours of cooling may protect an older person during a heat wave. In a control room, a few months above minimum power pool may create space for another runoff season to arrive. The intervention matters because time can prevent immediate failure. It remains incomplete because time does not guarantee recovery. The water moving south cannot decide whether next winter will be wet. It cannot repair every canal, lower every power bill, settle every water claim, or restore every depleted field. It can only change the sequence in which risks arrive, and that leads to the most important human question in the entire operation. When a system has enough water to postpone failure but not enough to restore security, who receives the delay, who absorbs the cost, and which small piece of infrastructure determines whether the protection reaches the person at the end of the line? The weak point is not the entire Colorado River. The weak point is a narrow band of water in front of several openings inside Glen Canyon Dam. That band separates ordinary operation from a system with fewer choices. It is easy to look at Lake Powell and imagine that the danger begins only when the reservoir appears almost empty. But the dam does not use every gallon equally. Its turbines, penstocks, outlet works, generators, transformers, control systems, and downstream channels were built around specific elevations and pressures. When the hollow surface falls, the reservoir can remain enormous, while the infrastructure connected to it becomes less capable. The weak point is not the amount of water the eye can see. It is whether the water is high enough to reach the pathway the system depends on. Under normal conditions, water enters 8 large penstocks, leading to the hydroelectric turbines inside Glen Canyon Dam. The reservoir provides hydraulic head, the vertical pressure that forces water through those conduits. The turbines spin. Generators convert that motion into electricity. The same water then exits below the dam and continues downstream. This pathway does several jobs at once. It produces power. It allows controlled releases. It supports revenue used for operations and regional programs. It gives managers a flexible way to adjust flows. As Lake Powell declines, all of those functions begin losing margin together. First, the lower water surface reduces pressure. The turbines receive less energy from each unit of water. Generating capacity weakens. The dam can still produce electricity, but it cannot produce as much as it could with a higher reservoir. That difference becomes especially important during periods when the regional grid needs flexible power quickly. Hydropower can respond to changing demand in ways that many other generators cannot. It can increase when solar production fades near sunset. It can help when extreme heat drives air conditioning demand upward. It can respond when another power plant unexpectedly goes offline. Every foot lost at Powell does not create a blackout, but every foot can reduce part of the flexible capacity available to prevent one. Then the reservoir approaches 3,490 feet above sea level. This is minimum power pool. The phrase sounds like a management target. It is actually a physical threshold. Below this elevation, water can no longer be released through the penstocks in the normal operating manner, and Glen Canyon Dam can no longer generate hydropower through its turbines. The generators do not stop because the lake is empty. They stop because the usable water surface has fallen too close to the intake system. Water remains behind the dam, but the primary pathway has been lost. That is the small component capable of changing the behavior of the entire system. The dam still has 4 river outlet works positioned lower than the penstocks. These structures provide another route for water to pass through the concrete. They are essential safety and operating features, but they are not identical replacements for the turbines. They do not generate electricity. Their total release capacity depends on reservoir elevation, because lower water creates less pressure. As the lake continues falling, the amount of water they can move also declines. A system that once released water through 8 power penstocks and produced electricity may be forced to depend on 4 lower outlets that provide no power and carry less flexibility. The map still shows a reservoir. The control room sees a reduced machine. This is why the 35-foot buffer above minimum power pool matters. The target elevation of 3,525 feet gives operators room to react before the surface reaches 3,490 feet. That room is not decorative. It absorbs uncertainty. Forecasts can change. Snowmelt can underperform. Dry soils can capture more water than expected. Summer heat can increase evaporation. Required releases can continue while inflow weakens. Equipment can need maintenance at the wrong moment. Without a buffer, every forecast error pushes directly against a physical threshold. A system operating exactly at its limit has no protection from being slightly wrong, but the target itself is only a line in a plan. The real weak point is the time required to defend it. Flaming Gorge is hundreds of river miles upstream. Water released there cannot appear at Powell immediately. It must move through the Green River and into the Colorado River. The release schedule must consider downstream ecosystems, river conditions, recreation, power operations, and the storage remaining at Flaming Gorge. If Lake Powell begins falling faster than forecast, managers cannot instantly add 1 million acre-feet by turning a single valve. The emergency response has travel time. The reservoir decline has momentum. The operational weakness is therefore both physical and temporal. The infrastructure needs water before the water can arrive. Imagine a hospital with backup oxygen stored in another city. The oxygen exists, trucks are available, but the hospital must recognize the shortage, issue the order, load the supply, move it across hundreds of miles, and receive it before the local tanks fall below a critical level. Flaming Gorge is not oxygen, and Lake Powell is not a hospital, but the timing problem is similar. A reserve is useful only if it can reach the weak point before the weak point loses function. This is why managers react to forecasts rather than waiting for the gauge to cross the line. By the time the emergency becomes visually obvious, the most effective response may already be too late. If Powell falls below minimum power pool, the first consequence is the loss of normal hydropower generation. That loss would not remain inside the dam. Electricity customers across the West receive power marketed from the Colorado River Storage Project. Other generators and market purchases would have to replace part of the missing output. Replacement power could be more expensive. During periods of intense demand, it could be harder to obtain. Utilities might absorb some costs temporarily, but costs eventually move through contracts, rates, public budgets, or reduced investment elsewhere. The failure of an intake becomes a pressure on a household bill. The second consequence is financial. Hydropower revenues support operation and maintenance of federal facilities and contribute to programs dealing with endangered fish recovery, salinity control, and other basin responsibilities. Less generation means less revenue. A low reservoir, therefore, does more than weaken one power plant. It can reduce the funding stream that helps maintain other parts of the river system. Concrete loses pressure. Turbines lose output. The power system loses flexible generation. Federal programs lose income. The chain begins at an elevation line almost invisible from the shoreline. The third consequence is operational. River outlet works can continue moving water below minimum power pool, but using them as the primary long-term release pathway would place the dam in a condition it was not expected to occupy routinely. These outlets have been used before, including during maintenance and special operations, but prolonged dependence at very low reservoir levels introduces narrower margins. Water moving at high velocity through tunnels and valves can create vibration, pressure changes, cavitation, and wear. Cavitation occurs when low pressure causes vapor bubbles to form and then collapse against a surface. Over time, that collapse can damage metal or concrete. Engineers monitor and manage these forces, and the existence of risk does not mean failure is inevitable. But the evidence supports a clear conclusion. Below minimum power pool, the system would rely more heavily on a smaller set of structures under conditions that become less forgiving as elevation declines. Then comes the next threshold. Near 3,370 feet, Lake Powell reaches dead pool. At that elevation, the reservoir cannot release stored water through the dam beyond the amount entering from upstream. The lake may still hold a substantial volume, but that volume sits below the usable gravity outlets. This is the deepest form of the same problem. The water has not vanished. Access to it has. Downstream flow becomes increasingly tied to current inflow rather than stored reserves. The reservoir loses its ability to smooth dry periods by releasing water accumulated earlier. A storage system becomes closer to a pass-through system. That would fundamentally change the role Glen Canyon Dam plays in the basin. But the weak point appears before dead pool. It appears when options begin disappearing one by one. First, generation capacity declines with hydraulic head. Then the turbines become unavailable below minimum power pool. The river outlet works carry the release burden. Their capacity declines as the reservoir falls. Revenue weakens. Replacement power costs rise. Maintenance decisions become more consequential. Downstream obligations remain. The system does not break in one dramatic moment. It becomes less flexible in stages. Each stage leaves fewer tools available for the next emergency. The danger is not only failure, it is the loss of recovery options before failure. The city of Page, Arizona, and the Lecce chapter of the Navajo Nation reveal how specific these vulnerabilities can become. Their water supply has depended on infrastructure connected to Lake Powell. As reservoir levels declined, federal crews completed a new intake connection designed to maintain delivery even if the lake approached dead pool. That project is evidence of adaptation. It is also evidence of the problem. A water supply serving real households had to be re-engineered because the original relationship between the reservoir and the intake could no longer be assumed. The weak point was not the whole municipal system. It was the height of an intake relative to a falling lake. Lower the water far enough, and a community can stand beside billions of gallons it cannot reliably reach. Recreational infrastructure follows the same geometry. Boat ramps were built to meet shorelines within an expected range. As Powell or Flaming Gorge falls, ramps can end above the water. Marinas may need to move. Access roads become longer or unusable. Search and rescue distances change. Businesses, depending on visitors, lose traffic. These impacts are not equal to losing hydropower or municipal water, but they demonstrate the same mechanism. Infrastructure remains fixed while the water moves away from it. The failure begins at the connection point. At Flaming Gorge, the weak point is different but connected. The reservoir is being asked to provide between 660,000 and 1 million additional acre-feet through April of next year. When supplemental releases began, it held about 3.01 million acre-feet and was approximately 82% full. The plan is designed to reduce impacts where possible, but every additional release lowers the reservoir relative to the path it would otherwise have followed. Ramps, habitat, hydropower, shoreline access, and future drought protection all depend on that elevation. Saving the weak point at Powell can place greater load on smaller weak points upstream. This is the anatomy of systemic risk. The system does not need every component to fail. It needs one critical component to lose enough capacity that pressure moves into the next one. If the penstocks lose access to water, the outlet works carry more responsibility. If hydropower declines, other generators carry more electrical load. If replacement power costs rise, customers and public programs carry more financial load. If Flaming Gorge releases additional storage, its future inflow must rebuild the lost cushion. If the next winter is dry, the system begins the following year with fewer reserves and fewer easy decisions. Risk moves from structure to structure, like water moving through connected channels. This is why the emergency releases matter and why they cannot solve Powell alone. They defend a specific weak point. They do not remove the conditions creating the pressure. The river remains dry relative to demand. Forecast uncertainty remains. Fixed infrastructure remains tied to elevation. Downstream responsibilities remain. The release can hold the water surface above an intake. It cannot redesign the dam, refill every reservoir, replace hydropower revenue, or guarantee the next snow season. It can keep one pathway open while the system searches for a longer answer. The weak point is not the whole Colorado River. It is the place where stored water must meet steel. But once that connection begins to fail, the consequences leave the dam almost immediately. They enter power markets, municipal intakes, environmental programs, tribal communities, recreation, budgets, and the next reservoir upstream. And this is not a theoretical chain invented for a future disaster. A version of it has already appeared before, when emergency water was released from Flaming Gorge to protect Powell, and the basin learned exactly what temporary rescue can and cannot accomplish. This is not only a reservoir emergency, it is a calendar failure. The Colorado River system was built around an expected sequence. Snow accumulates through winter. Runoff arrives in spring. Reservoirs capture the pulse. Water is released through summer and carried into the next year as stored security. That sequence has never been perfectly reliable, but the infrastructure, contracts, power systems, farms, cities, and operating rules were all designed around the belief that the cycle would remain recognizable. What is changing is not only the amount of water, it is the timing, efficiency, and reliability of the entire cycle. Snow can still fall while less water reaches the river. Spring warmth can arrive earlier and move the melt before reservoirs and users expect it. Dry soil can absorb the first part of the runoff. A hotter atmosphere can pull more water from land, vegetation, and open reservoir surfaces. The old calendar says snow becomes supply. The new pattern says snow must survive the journey first. That difference is now appearing inside federal operating plans. Flaming Gorge is sending water south because the normal seasonal inflow into Lake Powell may not arrive in sufficient volume to protect the dam. Powell is retaining more water because the system can no longer assume that the next runoff will repair the loss. Managers are using stored water to defend against a forecast failure in future water. This is not simply drought response. It is a shift from managing abundance across seasons to managing scarcity across thresholds. For most of the 20th century, the major reservoirs of the Colorado River were treated as enormous buffers. A wet year could be captured and carried forward. A dry year could be absorbed by releasing water stored earlier. Lake Powell and Lake Mead together allowed the system to separate the timing of precipitation from the timing of demand. Cities could grow, farms could plan irrigation, hydropower could be scheduled, downstream deliveries could continue even when one season underperformed. The reservoirs made the river appear more stable than the climate feeding it. But every buffer has a limit. When withdrawals and losses remain larger than replenishment over many years, storage stops acting like insurance and starts acting like income. The basin is not only using water that arrives this year, it is spending water that arrived in previous years. That distinction is the heart of the system pattern. A reservoir can hide an imbalance for a long time. The shoreline falls slowly. The public sees a lake that is still vast. Water continues flowing through dams. Electricity continues being generated. Deliveries continue reaching farms and cities. The system looks functional because storage is covering the gap. But the declining reservoir is evidence that present operations depend on the past. Each acre-foot released from long-term storage is a promise that future inflow will eventually replace it. When future inflow repeatedly fails to do so, the promise becomes debt. Emergency releases from Flaming Gorge reveal that the basin is now moving that debt between accounts. Powell carries an immediate infrastructure risk, so stored water is transferred toward Powell. Flaming Gorge loses part of its cushion. Powell reduces releases, so Lake Mead receives less than it would have under the earlier schedule. The immediate threat is softened, but the underlying shortage does not disappear. It changes location and timing. This is why a rising Lake Powell can coexist with a basin that remains under pressure. Local recovery is not system recovery. A reservoir can gain water because another reservoir is losing it. A critical elevation can be protected because a downstream release is delayed. The operating map can improve while the total balance remains weak. The system becomes harder to understand because success at one point may represent strain somewhere else. The headline shows Powell rising. The deeper pattern shows storage being repositioned around the nearest failure threshold. This is not only a water shortage, it is a margin shortage. The system is losing the spare capacity that allows mistakes. Dry forecasts, infrastructure outages, and extreme seasons to be absorbed without immediate consequences. Margin exists in several forms. It is the vertical distance above a turbine intake. It is the water held behind an upstream dam. It is the generating capacity available when demand rises suddenly. It is the unused space in a municipal budget. It is the groundwater available when surface deliveries weaken. It is the number of years a farm can survive reduced production. It is the time between one emergency and the next. As those margins narrow together, small disruptions become more powerful. A weak snow season that once would have been absorbed by reservoir storage can now trigger operating changes across several states. A hot summer that once increased demand may now coincide with lower hydropower output. A maintenance outage at a dam becomes more difficult when every turbine matters. A legal disagreement becomes more urgent when there is less water available to divide. The risk is compound because each pressure reduces the capacity to handle the others. This is also a recovery failure. The system has repeatedly shown that one wet year can improve conditions quickly. Snowpack increases, runoff rises, reservoirs gain elevation. Emergency storage can be recovered. The visual transformation is dramatic, and that drama encourages the belief that the crisis has ended. But hydrologic recovery is not always institutional recovery. A wet year does not automatically change demand. It does not redesign intakes. It does not settle unresolved water rights. It does not guarantee that the next dry sequence will be shorter. It does not restore every groundwater basin, repair every canal, or replace every dollar lost during the previous shortage. The reservoirs may recover faster than the system built around them. Then another dry period arrives, and the same emergency tools are activated again. Rescue becomes a cycle. Water is transferred. Elevation is protected. A wetter period restores part of the storage. Pressure returns before the underlying rules and infrastructure have changed enough. The danger is not that emergency releases fail every time. The danger is that they succeed just well enough to postpone decisions the basin cannot avoid forever. Every successful intervention can create the appearance that the existing system remains workable. In the narrow sense, it does. Water still moves, dams still operate, power still reaches customers. But the cost of maintaining that continuity rises. More storage must be shifted. Release plans must be changed earlier. Forecasts must be watched more closely. Infrastructure must be modified to operate at elevations once considered unlikely. Communities must prepare for shortages that used to be treated as exceptional. A system that requires increasingly aggressive intervention to produce the same outcome is not stable. It is compensating. The old operating calendar is also being tested by temperature. River management traditionally focuses heavily on precipitation because snow and rain supply the water, but temperature determines how much of that supply survives. Warmer conditions can increase evaporation from soil and reservoirs. Vegetation can use more water during a longer growing season. Snow can melt earlier, changing the timing of runoff. Dry ground can capture more of the melt before it reaches streams. This means the same amount of precipitation can produce a different amount of usable river flow. The basin may receive weather that appears familiar while producing hydrology that is not. That is one reason historical averages become less reassuring. An average built from a cooler period may not describe how water moves through a warmer landscape. The number on the snow map can look normal. The number at the reservoir can still fail. This does not mean every low runoff year is caused by one factor, or that future flow can be predicted with perfect confidence. It means the conversion between precipitation and supply is becoming more important than the precipitation total alone. The infrastructure was built to store runoff. It cannot store snow that evaporates, enters soil, or is used by vegetation before reaching the river. The dam begins working only after the landscape has taken its share. That creates a new baseline of uncertainty. Water managers have always operated under uncertainty, but the range of plausible outcomes becomes more consequential when reservoirs are low. At high storage, a forecast error can be absorbed. At low storage, the same error can move Powell several feet closer to minimum power pool. The lower the margin, the more valuable accurate forecasting becomes, and the more damaging surprise becomes. Yet, forecast uncertainty cannot be eliminated. Weather remains variable. Soil conditions are difficult to measure across enormous mountain regions. Runoff can change quickly. The system therefore faces a paradox. It needs more precision at exactly the moment when the physical environment is becoming less reliable. That pressure changes preparation. Emergency planning can no longer begin, only when a reservoir reaches a visibly alarming level. Water released from Flaming Gorge requires travel time. Infrastructure modifications require design, funding, and construction. Power replacement contracts must be arranged before generation disappears. Municipal intakes must be extended before the lake falls below them. Farmers must choose crops before final runoff is known. Tribal communities need infrastructure years before the next emergency. The preparation calendar must move earlier because the consequences arrive after long delays. The event is happening now, but the decisions capable of changing it often had to begin months or years earlier. Risk will also migrate. A release that protects Powell may shift concern toward Flaming Gorge. Reduced releases from Powell may place more pressure on Lake Mead. Lower hydropower can increase dependence on other generators during extreme heat. Higher energy costs can affect pumping and water treatment. Reduced storage can weaken recreation economies. Changes in river flow can alter habitat conditions. The next system failure may not appear where the original shortage began. Water connects the components, but scarcity transmits through finance, electricity, ecology, transportation, and public health. The basin is not a line of reservoirs, it is a network of dependencies. That network is why Powell cannot be saved by emergency releases alone. Flaming Gorge can provide water. It cannot provide a permanent balance between supply and use. Glen Canyon Dam can retain more storage. It cannot guarantee future snowmelt. Forecasts can identify danger. They cannot create operating margin. New intakes can preserve access at lower elevations. They cannot make the reservoir full. Every technical solution protects a function. None removes the larger equation. The future will depend on whether the basin can reduce the rate at which it spends stored water, improve infrastructure for lower and more variable conditions, and build agreements that respond before reservoirs approach physical limits. The current operation is therefore more than an emergency maneuver. It is a preview. It shows how the basin may function when thresholds, rather than abundance, control decisions. It shows water being moved not toward the place of greatest demand, but toward the point of greatest immediate vulnerability. It shows the difference between keeping a system alive and making it secure. The release from Flaming Gorge may hold Powell above minimum power pool. The reduced release from Powell may preserve another layer of elevation. A future wet year may restore some of what has been spent. But if the operating model continues, requiring stored water to cover a recurring gap, the next emergency will begin with less room than the last. That is the future echo already visible in the present. The question is no longer whether one reservoir can rescue another. The question is how many times the basin can move the same shrinking margin before there is nowhere left to move it from. The warning does not need exaggeration. The evidence is already enough. Flaming Gorge is sending additional water south. Lake Powell is retaining more water than the original operating schedule called for. Federal managers are doing both because credible forecasts showed Powell approaching elevations where Glen Canyon Dam would lose hydropower and face reduced release capability. Those statements are supported by official plans, reservoir models, and physical thresholds built into the dam. But several other statements would go beyond the evidence. The emergency release does not prove Lake Powell will cross minimum power pool. It does not prove the dam will fail. It does not prove the Colorado River will stop flowing below Glen Canyon. It does not prove every farm loss, electricity bill, ecological change, or municipal problem in the basin was caused by this operation. And it does not prove that one future season will follow the driest forecast now on the screen. The difference between warning and certainty is the evidence line. On one side of that line are facts. Between approximately 660,000 and 1 million acre-feet of additional water is being delivered from Flaming Gorge toward Powell through April of next year. When those releases began, Flaming Gorge held about 3.01 million acre-feet and was approximately 82% full. The annual release from Lake Powell was reduced from 7.48 million acre-feet to 6 million acre-feet. Glen Canyon Dam was not designed to operate normally below minimum power pool at 3,490 feet. The drought response target of 3,525 feet exists to provide a 35-foot buffer above that threshold. These are not predictions, they are operating decisions and physical measurements. On the other side of the line are outcomes that remain uncertain. How much of the planned upper limit will ultimately be released? How much water will reach Powell under changing river conditions? How strong the next snow season will be? How efficiently that snow will become runoff? Whether future inflow will replace the storage removed from Flaming Gorge? Whether Powell will remain safely above minimum power pool under the most probable path, the driest path, or some path between them? These questions cannot be answered honestly by turning a model into a promise. Forecasts describe possible futures. They do not command the weather. That uncertainty does not make the emergency meaningless. It explains why the emergency exists. Operators are acting because the cost of waiting could be larger than the cost of moving water early. If the basin becomes wetter than expected, the intervention may preserve more margin than ultimately proves necessary. If the basin remains dry, the operation may be the difference between keeping normal hydropower available and entering a more restricted operating condition. The action is not evidence that catastrophe is certain. It is evidence that the risk is serious enough to justify spending stored water before certainty arrives. That distinction matters because public discussion often moves toward one of two extremes. One extreme says, the release will save Lake Powell. The other says the system is already collapsing. Neither statement captures the evidence. Flaming Gorge can help Powell. It cannot solve Powell alone. The release can change the elevation trajectory. It cannot guarantee recovery. The reduced outflow at Glen Canyon can retain more water in Powell. It also changes what moves toward Lake Mead during the same period. The basin can defend one reservoir without becoming wetter overall. These facts are less dramatic than a promise of rescue or a prediction of collapse. They are also more important. The evidence shows a system redistributing risk. Powell is closest to a critical infrastructure threshold, so water is being concentrated there. Flaming Gorge gives up part of its stored cushion. Lake Mead receives less than it would have under the previous release schedule. Power operations gain time. Upstream storage loses time. The action may be rational and necessary, while still revealing the depth of the underlying problem. A healthy system does not repeatedly need to move emergency reserves toward the same weak point. A stressed system does. It is also important to separate climate influence from individual causation. Rising temperatures can reduce runoff efficiency, increase evaporation, dry soils, alter snowmelt timing, and place greater pressure on water systems. Long-term warming is relevant to the Colorado River Basin, but no single forecast, reservoir decline, or emergency release can be explained by temperature alone. Precipitation variability matters, multi-year drought matters, water use matters, reservoir rules matter, legal obligations matter, agricultural demand, municipal growth, conservation, groundwater use, and operating choices all matter. The basin's risk is created by these forces interacting. Saying that does not weaken the climate signal. It prevents the climate signal from being turned into a universal explanation that ignores management and demand. The same boundary applies to human impacts. A farmer facing a poor season may be affected by local water rights, market prices, soil conditions, heat, debt, and many other factors. A household facing a high electricity bill may be responding to fuel prices, utility investments, market conditions, and extreme demand, not simply lower hydropower at one dam. A recreation business at Flaming Gorge may see changing visitation for reasons beyond reservoir elevation. These outcomes can be connected to the larger system without being attributed to one valve opening in April. The honest claim is that shrinking water and energy margins make people with fewer alternatives more vulnerable. That is enough. The warning does not need a false chain of certainty. The physical risk at Glen Canyon Dam must also be described precisely. Falling below 3,490 feet would end normal hydropower generation through the turbines and reduce the dam's ability to release water. It would not mean the dam instantly becomes useless. Lower river outlet works can still pass water. Falling farther toward approximately 3,370 feet would create a more severe constraint known as dead pool, where only water entering the reservoir could continue downstream. Even then, the correct language is loss of operational capability, not sudden structural collapse. The dam is not predicted to break because the reservoir is low. The danger is that a massive storage and power facility can retain water while losing access to the pathways that make that water useful. That is the real weakness. It is quieter than a dam failure. It is also more plausible. Another evidence boundary surrounds the future operating rules. Federal agencies are evaluating alternatives for how Lake Powell and Lake Mead should be managed after the current guidelines expire. That process shows official recognition that the old operating structure cannot simply be assumed to fit future conditions. But a draft environmental review is not a final agreement. It does not establish which alternative will govern the river. States, tribes, federal agencies, water users, environmental groups, and Mexico still hold different interests and legal positions. The existence of alternatives proves that change is being considered. It does not prove what that change will be. Any claim that the basin has already chosen a permanent solution would be premature. What can be said is that the current emergency is arriving while the future rules remain unsettled. The system is making immediate decisions with temporary tools while negotiating a longer operating framework. That timing creates its own risk. Reservoirs respond to snow and heat continuously. Institutions respond through meetings, law, modeling, consultation, and negotiation. The river can lose elevation faster than an agreement can be written. Flaming Gorge releases are therefore both an engineering action and a message from the calendar. The physical system is already demanding decisions that the political system has not completed. That does not mean agreement is impossible. It means delay has a measurable form. It appears as feet of lost elevation and acre-feet removed from reserve storage. Now return to the opening image. Water is leaving Flaming Gorge. It enters the Green River, travels hundreds of miles, joins the Colorado, and moves toward Lake Powell. From a shoreline, it may look like rescue. From a control room, it looks like an adjustment. From the full basin, it looks like stored margin changing location. The movement is real. The relief may also be real. Powell can remain higher because of it. Glen Canyon Dam may continue producing power because those additional feet stay above the intakes. Downstream operations may retain options that would otherwise narrow. These are meaningful benefits. They deserve to be understood without being dismissed as symbolic. But the same water cannot protect every reservoir at once. It cannot remain behind Flaming Gorge and arrive at Powell. Water retained at Powell cannot move to Meade during the same period. A stored acre-foot can defend one position at one time. The emergency is a choice about where that defense matters most. This is not just a reservoir release. This is a system buying time with water it cannot replace on command. That sentence has followed the entire story because it contains both the value and the limit of the operation. Time can be decisive. It can preserve hydropower. It can protect municipal access. It can allow another runoff season to arrive. It can create space for new operating rules, conservation agreements, infrastructure projects, and difficult negotiations. Time is not nothing. In an emergency, time can be the most valuable resource available. But time becomes dangerous when it is mistaken for supply. A higher Powell created by transferring and retaining water does not mean the basin has produced more water. A wet season does not guarantee the next one. A successful emergency release does not prove the same source reservoir can rescue Powell again under worse starting conditions. A 35-foot buffer does not become permanent merely because it was protected once. Every success must be measured against what it consumed, and whether that margin can be rebuilt. The future of the Colorado River will not be determined by whether operators can move 1 million acre-feet one time. It will be determined by whether the basin can stop requiring emergency transfers to preserve ordinary function. It will depend on whether water use, reservoir rules, infrastructure, and expectations can adjust to a river that may deliver less reliable runoff than the system was built around. It will depend on whether tribes and communities receive the infrastructure and authority needed to participate fully in that future. It will depend on whether cities, farms, power systems, and governments treat storage as a limited reserve rather than an invisible extension of annual supply. None of those outcomes is predetermined. The basin has technical skill, monitoring systems, legal tools, conservation capacity, and evidence from earlier emergencies. The current action itself proves that institutions can coordinate before a threshold is crossed. The warning is serious, but it is not a declaration of helplessness. The system still has choices. The number of choices is what is shrinking. The event will pass. The release schedule will end. The water now moving through the Green River will eventually become part of another reservoir calculation, another power schedule, another downstream flow. But the thing this operation revealed will remain. Lake Powell can be protected temporarily by drawing down another reserve. A dam can keep functioning while its margin becomes dangerously thin. A reservoir can rise while the basin becomes no wetter, and a system built to smooth the natural cycle can begin consuming its own ability to survive the next one. The future will not be decided only by the peak elevation at Powell or the final volume released from Flaming Gorge. It will be decided by whether the system can rebuild its margin before the next load arrives, because the water is moving south now. The unresolved question is whether the basin is moving with it.